Hi everyone, and welcome to YEA's F equals MA lecture series. This is the third lecture, which will focus on kinematics in more than one dimension. Oop. Yeah, okay. So first, let's do some review from last time's lecture. So in one dimension, we have a particle moving on a number line. And at some time t, it can occupy a position x. And so the position, and as time goes on, it can change. So the position is just a function of time. So we can also define the displacement as overall change in position, like that. And the distance is the length of the object's path, which is also the magnitude of the displacement. And this is true for 2 dimensions as well. We'll see this later on as we get into vectors. And we defined velocity as the rate of change of position, which is delta x over delta t, or in terms of calculus, it's dx dt. And acceleration is similar. It's the rate of change of velocity, so it's dv dt. And with those, we derived these 2 equations of motion, which is we just derived by integrating those 2 equations. And from these, we can also derive others, like 2 common ones down below. And there's also gravity, which we'll see a lot in 2-dimensional problems. And any object falling near the center of the Earth will have a constant acceleration of 9.8 meters per second downwards towards the center of the Earth. All right. Now let's go to 2 dimensions. So first, to talk about stuff in 2 dimensions, we have to talk about vectors and scalars. And I want to ask you first, how many people are familiar with vectors and scalars? Okay, so I see a few of you said you're familiar with these. So I'll just go over these quickly to make sure everyone understands. So in 1 dimension, we just represented position with a number. But in 2 dimensions, it's slightly different because we can't just represent the position with a single number. We need 2 coordinates. So there's common coordinate systems like Cartesian coordinates, where each point is just an XY coordinate pair. Or you can also use polar coordinates, so in terms of r and theta. And we say that these quantities where you need like 2 coordinates because it has a direction to it, we call them vectors. So vectors have a magnitude, which is sort of like their length, and they also have a direction. And this is different from scalars, which only have a magnitude. They don't have direction. And the easiest one so far to look at is Cartesian coordinates. So we'll be using Cartesian coordinates in this lecture and throughout most of kinematics. So again, here's just some examples. You can see these points aren't like they're on a plane. You can't just represent them with a single number. All right. And let's see. Shoot, where can I annotate? All right, so we can see that the vectors here, if I can figure out how to annotate here. What? There's no annotate button. Anyways, the vectors here would just be from, I guess, the origin to whatever that point, wherever the point is, that's the position vector. And there are lots of quantities that are vectors and scalars in physics. So, for example, you have position's a vector, but we can also say velocity and acceleration are vectors. And because velocity is the derivative of position, so the time derivative of a vector will give another vector. And acceleration is the derivative of velocity, so it's also a vector. And we have distance and speed that we talked about briefly in the previous lecture. These are scalars because we're taking only the magnitude or the absolute value of the position and velocity. And we can categorize many quantities in physics as either vectors or scalars. So some common vectors you'll see later on are force and momentum. And there's some common scalars like energy and power. All right, let's talk about components. So we can express vectors in terms of components. They're like, so the black vector here is actually the sum of the green and blue vector. And the green and blue vector are kind of nice to deal with because one's only going along the x direction, and while the other one's only going along the y direction. And you'll see that this becomes useful as we get into 2D problems later on. And the magnitude of a vector is just its length, and you can calculate it from its components. So, for example, this vector here has the green vector, has length 2. So it's like 2 along the x-axis. And the blue one has length 3. So the total length of the vector, you can use the Pythagorean theorem and it comes out to be root 13. And there are lots of different notations for vectors. These are just a few. These I hat, j hat, x hat, and y hat, those are called unit vectors. And they're basically vectors with length 1. And I hat just represents, I hat and x hat both represent like a vector of unit length 1 that's along the x direction. And j hat and y hat are vectors of length 1 that point along the y direction. And when you're writing down vectors as like variables, they're usually written with an arrow if you're like handwriting them, or if you're typing them, you can also type them in bold font. All right. And let's see what operations we can do with vectors. Well, we can add vectors by putting the tail of one at the tip of the other. So you can see in this picture, the black vector is the sum of the green and the blue vectors. And in terms of the components, you can see why we wanted to express vectors in terms of components, because to sum our two vectors, now we can just sum the two components to get our final vector. So for example, if you have the vector 1, 2 and 2, 1, the sum becomes 3, 3. Oh shoot. And multiplying vectors, you can also multiply vectors by a scalar, and that just basically scales it up. So we see this vector is multiplied by 2, it's in the same direction, but it's just twice as long. And if you multiply it by like -2, it's the same, but the direction's reversed. And in terms of components, we just multiply each component by whatever we're multiplying the vector by. So if we have 1, 2 and we multiply it by 2, it becomes 2, 4. And there are other ways to multiply two vectors. So there's the dot product and cross product, and we will go into them later. But for now, just know that they exist. All right, so let's move on to some problems in 2D. Practically speaking, the easiest way to solve a problem is not like doing algebra with vectors. It's just considering each component of the vector separately. So we want to first break down all the vectors into their components, and each dimension will act independently from the rest of the dimensions normally. So we can use the equations of motion for each component separately. And so, for example, say you have constant acceleration a of x in the x direction, and we have constant acceleration a of y in the y direction. Well, we can write two equations of motion here for the x direction, and there are also two equations for the y direction. And the equations for the x direction don't have any variables relating to y, and the equations for the y direction don't have any variables relating to x. So what this means is that we can just solve them separately, and then we won't have to worry about dealing with vectors or doing algebra with them, I guess. So yeah, each dimension is completely independent from the other. Like if there's a constant acceleration a of x in the x direction, we can just write x of t is x0 plus v0t plus 1/2 at squared. And it doesn't depend on what's going on in the y direction. So it could be staying completely still in the y direction. It can be moving with constant y velocity, or it can be even oscillating around in the y direction. That all doesn't matter. As long as there's a constant acceleration in the x direction, this equation still holds. All right, let's do some examples. And I will give you a few minutes to look at these. And as always, if you have any questions that you can always ask me, or you can send me your answers in the chat. All right, so it's been a while, and so I will go over these problems now. So the first one is just they will hit the ground at the same time. And well, yeah, I see someone here's um considering whether or not the Earth is flat. I guess that's a valid concern, but yeah, I was assuming that the Earth is approximately flat, so they will hit the ground at the same time because, as we said earlier, the two dimensions are independent from each other. So the motion in the horizontal dimension doesn't affect the motion in the vertical direction at all. So they will both be accelerating at the same rate in the vertical direction, which means that, and since they started from the same height, that means that they will hit the ground at the same time. And the second one's sort of a similar problem. It's so the hunter will hit the monkey. And this is because if the monkey didn't drop, first of all, the bullet will have fallen slightly due to gravity. But since the monkey did drop, the amount that the bullet falls is actually the exact same distance that the monkey falls because they've been falling for the same time basically. So that means that the monkey will end up where the bullet will end up, and so the hunter will still hit the monkey. All right. Now let's go on to projectile motion. And so projectile motion is a classic example of 2D kinematics. In the most simplest case, we have a projectile that's fired at an angle theta above the horizon. And so we want to figure out stuff about this projectile. So, for example, how far does it travel? Well, let's think about what's going on here. So assuming there's no air resistance, there's only gravity that acts on this object, right? So in the x direction, there's no force that acts on the object. And we'll learn about forces later, but that just means that the projectile will continue in the x direction at a constant velocity. So there's no acceleration in the x direction. And in the y direction, it's just gravity. So there's a constant acceleration of g downwards. All right, so let's do a walkthrough. So how this is going to work is I'll just guide you through the steps of the problem, and I'll give you a few minutes for this first step. Just if you have any questions, ask me or send me your results to the first step in the chat. And after a few people are done, I will move on to the second step. Okay, I'm going to, I guess I got a few responses, but not that many. So I will give you guys first a hint, which is if you remember from a couple of slides ago, the equations of motion are just delta x is equal to v0 t plus 1/2 at squared. Hold on. Okay. And okay, another hint would be, so this, I wrote delta x here, right? But this equation's really for any dimension that has a constant acceleration. So you can use this for x and you can use this for y as well. All right, so it's been a while, so I will just tell you this first step, which is to just use this equation. And so if we think back, what what was the acceleration in the x direction? Well, there was no acceleration in the x direction, right? So this is just zero. And what's the initial velocity in the x direction? Well, if we consider the vector here, the initial velocity vector, well, it had an angle of theta to the horizontal, right? So if you know a little trigonometry, we can use it to find the components. So what's this component here? Right, so if we take the velocity and we split it into components, we'll have a v cosine theta here. And similarly, the vertical component will just be v sine theta. All right. So now let's see. We can replace this v0 here with a v cosine theta. And what happens in the y direction? Well, in the y direction, we have the same equation. We have delta y, uh, delta y is equal to, now it's v sine theta. And now we do have an acceleration, which is negative g. So these are the two equations of motion. All right, now what's the second step? We have a system of equations here, but we have a problem, sort of, because we have a few unknowns. We know v and we know theta, but we don't know what delta x is, and we don't know what delta y is, and we don't know what t is. But there is one condition that we haven't used yet. So what is this condition that we haven't used? Yes, and as a bit more of a hint, um, if we look at the trajectory of our projectile, oh, let me move this up here. So if this is the trajectory of our projectile, what's so special about this point here? What's one condition about what this point is that we can write an equation? All right, yeah, so it's just y is equal to 0. So now we have our third equation, which is that y is equal to 0. So now what do? We have to solve this. So I'll just give you a few more minutes here and solve this equation and tell me the solution. All right, it's been a while now. Yeah, it's been a while now, so I will go over the solution. To solve the system, it's just algebra. So we have three equations, and our unknowns are delta x, delta y, and t. All right, so first of all, we have delta y is 0. That's just one of our equations. So now we can substitute that in here. So what we get is 0 is equal to v sine theta times t minus 1/2 gt squared. So now what happens here? Well, we only have one unknown left in our equation, is t. So we can solve for t. And what we do is we divide by t on both sides, and we can also move this to the other side. So we'll have 1/2 gt is v sine theta, or this just becomes t is equal to 2v sine theta over g. All right. Now, for the final step, we need to plug it back in here, and that will give us delta x is equal to b cosine theta times 2v sine theta over g. So this is 2b squared sine theta cosine theta over g. And if you want, you can also write this as v squared sine of 2 theta over g. All right, so that's just our answer. Yeah, and that's, if you go back to our problem, go back. Yeah, that's our answer, because if you think about it, it's just the x coordinate here. That's just the length. The delta x from here to here, that's how far it travels. And so this would be our answer to the question, basically. All right. Now I have a few more practice problems that I've prepared. Uh, uh, how do I delete this? Let's just do this. Yeah, okay. So here are the problems, and I'll give you a few minutes to work on them. As usual, you can always ask me questions if there's anything you're confused about or you're stuck on. And you can send me answers or your thoughts in chat. Actually, since it's close to 2:45, which is about an hour after I started, I will just give you our normal 10-minute break. So I will be back at uh around 2:55. In the meanwhile, please work on these problems, and at 2:45 you can take your 10-minute break. And please send me questions or your answers or whatever you want to say about the questions, I guess. All right. So it's 2:55 right now. So that's the end of our 10-minute break. And I see that a few people have sent me answers, which is nice. So I will start giving hints on these problems. So for the first one, let's first write down the equations of motion for the projectile, just sort of like what we did before. So what are the equations of motion for this projectile? Anyone? We just did this. What are the equations of motion for the projectile? All right, yeah, so we can just write the same ones from last time actually, which are just delta x equals v cosine theta t, and delta y is v sine theta t minus 1/2 gt squared. All right, so now we have these two equations of motion, and we have sort of two things we want to find, right? We want to find its maximum height h, and we want to find the distance it travels r. Well, actually, we've already found one of these in a previous problem. Does anyone remember what the range of the projectile is? How far it travels? Yeah, okay, good. So I will write it as 2v squared sine theta cosine theta over g. This is r. It's also v squared sine 2 theta over g. And so now what we want to do is find h. So what is the height? What's the maximum height our projectile reaches? And this one's a bit trickier. And if you remember in our walkthrough last time, actually what we did was we had two equations and three unknowns, right? So we imposed another condition, which is that delta y is equal to 0. But now, if we want the maximum height, delta y is no longer equal to 0, so we can't just use that equation. But there is a different equation that we can write when it's at its peak height. And so what is this equation? X equals r over 2. Um, yes, that is correct. I guess that's one way of solving it, which is if you look at the path the projectile takes, well, this is symmetric, right? So if this is R, then the maximum height, the vertex here, must be at R over 2. But so this works here, but it's actually uh it's not always the case because if our path's not symmetric, let's say I don't know. If we're throwing it off a cliff, then this is going to be different. Like we can't just use R over 2 for this case. All right, yeah, some people are saying, telling me, yeah, so basically the idea here is that we want the velocity in the y direction to be equal to 0. And why is this? Well, let's look at the velocity for a second. Let's say at this point, the velocity points this way, and as it goes up, it starts pointing this way, and then at the very top, it points this way. And at the very top, the velocity is just completely horizontal. And why is this? Well, let's think about what y velocity really means. Well, the y velocity is the rate of change of its height, right? So as long as the y velocity is positive, it's still going up. But we know that it's accelerating downwards, so the y velocity is decreasing. So at some point at the top, it's going to reach 0. And then after that, it's going to start going down. So at first it's positive, the y velocity is positive, then it goes to 0. And then after that, it's negative. So the height starts decreasing. Well, where's the maximum height? It's just when the y velocity is 0, where it's no longer increasing anymore. That's where it's at the maximum. All right. So that's our second equation. I mean, our third equation, which is Vy equals 0. And after we have this equation, there are a few ways to solve it, I guess. You can bring up some of our other kinematics equations. Um, Two of them, actually. You can use, I see someone suggested V final squared equals V initial squared plus 2A delta Y in our case. Or you could just use V equals V0 plus AT. I'm going to stick with this one because I like it more. So let's see. What is our V0? Well, we decided that it's V sine theta. And our A is negative G. And we just reasoned that our V final should be 0. So now what we can do is we just solve this equation for V. We get V is GT over sine theta. Wait, no. We solve for T, sorry, my bad. All right, we solve for T, which is V sine theta over G. Because T's are unknown and V is given. All right, well, let me go back to the slide here. All right. So what does it want us to find? Well, we want to find the height h, which is just our y coordinate. So we plug this back into our equation here. So we will get delta y, which is our h. Hold up. Our delta y, which is our h, it's equal to v sine theta t, and t is just v sine theta over g, minus 1/2 gt squared. All right. And then we can do some algebra here and simplify this. So this just becomes 1/2 v sine squared theta, v squared sine squared theta over g. All right. So what do we want here? We want, let me switch to my screen only. So we want that h is greater than r. If we go back to the problem, it says that we want when it rises to a height which is larger than the horizontal distance that it'll travel when it returns to the ground. So that's basically saying that h is greater than r. So now we know our h, it's 1/2 v squared sine squared theta over g. And we know our r, it's 2v squared sine theta cosine theta over g. And now you can probably see why I wrote it that way, because the v squareds cancel out, the g's cancel out, and the sine thetas cancel out. So what are we left with? We're left with sine theta is greater than 4 cosine theta if we bring the 2 to the other side. Or basically theta is just greater than arctangent of 4, which is approximately 76 degrees, as many of you have got. All right. Now that I've explained this problem, I will go back to the second problem. I'll give you a little more time to think about this problem. A few of you have sent me solutions, but so far, I don't think I've gotten any correct answers yet. So keep on thinking about that. And read the question carefully, of course. That's important. All right, so I've drawn a diagram of the problem here. We can see that the the cannon is fired at a cliff that's 150 meters away. That's the horizontal distance. And it's fired at a target. So it's fired directly at a target, which means that the target is exactly at a 60-degree angle away from where it's fired. So the target's right here. But actually, because of gravity, the path of the projectile looks more like this curved line here. And so it ends up here. And the problem's asking you for this distance. And yes, if you're getting something close to 45, you're probably doing something wrong. I would double check your work. Wait, actually, no, let me double check my work too. Um, oh wait, sorry. Yeah, okay, my bad. So originally the problem contained a diagram, and I did not copy the diagram, and apparently I interpreted the problem wrong. So, okay, oh, my bad. Okay, yeah. All right, so it's actually this distance that's 150 meters. So, yeah, 45 meters would be correct if this was the 150-meter distance. But actually, it's the target that's 150 meters away. Um, yeah, okay, then that makes more sense. All right. So I guess I'll just go over the problem then. Um, yeah, okay, then that's so the correct answer is around 11 meters. And how do we get this? Well, let's think. So let me do another walkthrough this time. So first, tell me what the equations of motion are for this projectile. That's sort of going to be a good strategy whenever you're given this type of problem. Just first write down the equations of motion. All right, so can anyone tell me what the equations of motion are for this projectile? And actually, it shouldn't be too hard because we've done this 2 times already, and they're basically the same. All right, let me go here and write them down. So we have the delta x here, it's the same since there's still no acceleration in the x direction. We have v cosine theta times t, and delta y is v sine theta t minus 1/2 gt squared. All right, so now the second step is usually to find another constraint, because right now we've written down our equations of motion, but we're still missing one equation, right? We have three variables, two equations. So what's our next equation? Yeah. So our next condition, this point, what makes this point unique is that this point is on the wall. It's on this wall, which means that it has to be this, whatever this distance, that's what its delta x has to be, right? So we can just use trigonometry to find that. Since we know this angle is 60 degrees, we know that this has to be 150 cosine 60. And maybe since I want to keep everything in variables for now, let's call this d. And so this will be d cosine theta. All right, so now we have our third equation, delta x equals d cosine theta times t. So now, how do we solve this? Well, three equations, three variables. We should be able to solve this. So I'll give you a few more minutes, and when you're done, please send me your solution. Or if you have any questions, please ask. All right, so it's been a few minutes. Let's just talk about this. So what are our unknowns here? We have delta x, delta y, and t. So let's first eliminate one of them. Let's take these two equations because they look nicer. Well, we can substitute one in the other. Shoot, my bad. To get d cosine theta is equal to v cosine theta times t. Well, now we can just Cancel out cosine theta and solve t equals d over v. Okay, so now what can we do? Well, we can plug this back into the second equation. So now what do we get? We get y is v sine theta v sine theta times t, which is d over v, minus 1/2 gt, which is d over v squared. So this is d sine theta minus 1/2 g d squared over v squared. And finally, what does the problem ask us? Well, it asks us to find this distance here, right? And so what we have here are y we defined as this distance here. So we want this big distance minus our y. And to find the height of the target, we can use trigonometry again. If we have this is d and we know this theta, it's just d sine theta, right? Okay, so now we want d sine theta minus delta y. And this is going to be our answer. So we plug this in. And you can see where we left stuff in variables because now the d sine thetas just disappear. And we're left with 1/2 g d squared over v squared. And that's our final answer. It's pretty nice. And this will be, in fact, 11.25, I'm pretty sure. Or, yeah, 11.25 if you use g equals 10. It's just 11 if you use g's 9.8. Yeah. All right. Now I have one final problem before we end here. So this is a slightly trickier problem, I would say, but just follow the steps. So first, wait, sorry, I'm probably not showing it here. All right, now I'm showing it. All right, this is a slightly trickier problem, but just follow our steps of first write down the equations of motion. Then, since you're lacking one equation probably after you do that. So what you need to do is find a condition that gives you your third equation. And then after that, you can just use algebra to solve the system of equations. And that's generally a good approach to approaching these types of problems. So yeah, and if you have any questions, please send me a message in chat. Otherwise, yeah, so first write down the equations of motion and send your answers to me. All right, so it's been a few minutes and no one sent me equations of motion, but that's fine. I will just give them to you since they're the same as last time anyways. So the equations of motion are delta delta x is v cosine theta times t, and delta y is v sine theta times t minus 1/2 gt squared. Still two. Okay. So now tell me, what is the condition here? What's the third equation we can write so that we can solve our system of equations? The equation of the inclined plane. Yes, that's basically correct. Yes, so what we want is that when it's in this area, like over here, that's basically when it's in the inclined plane section, right? The equation would be y y is equal to d2 over d1x. Yeah. And then what makes this problem a bit trickier is that there's a plateau after that. So this equation is actually only valid whenever x is between 0 and d1, right? So when x is greater than d1, what's our equation? Yeah, so we need to write a piecewise function, basically. So when x is greater than d1, what's our equation? Well, it's basically just d2, right? So these are our two pieces, so to speak. All right, so given this information, now I'll give you a few more minutes to solve solve the system of equations, and tell me what you get. All right, so if you're having a bit of trouble solving the system, that's fine. I'm going to give a slight hint right now. So, um, let's see what we have. We have our system, but our system of equations contains a piecewise function, which is sort of problematic. So what we do is just first solve this, like assume that 0 is less than x less than d1. So assume this equation's true. Now you solve the system delta x is v cosine theta times t. Delta y is v sine theta t minus 1/2 gt squared. And delta y is d2 over d1 times delta x. So solve this equation and tell me what you get here. Oh, what is d2 and d1? Do you mean the values or what they represent? Oh, the values? Um, okay, I will put them up here. It's going to overlap with my writing. Okay, so D1 is 6, D2 is 3.6. Maybe I'll just send them here. D1, 6, D2, 3.6. And then I'll go back to my system of equations. All right, and when you're done, please send me your answers in the chat. All right, yeah, since we're a bit short on time, maybe I will just walk through solving it. So what should we get here? Well, let's plug in these two equations into our third equation. So we get v sine theta times t minus 1/2 gt squared is equal to d2 over d1 times v cosine theta times t. So now we have a factor of t we can cancel out. And while we're at it, let's multiply both sides by d1. So d1 v sine theta minus 1/2 d1 g t d2 v cosine theta. All right, now the only unknown left in our equation is just t. So we can solve for t easily. Just bring it out. T becomes dv sine theta minus d1 d2 v cosine theta divided by 1/2 d1 g. And if you plug this into a calculator, hold on, you should get around 0.625 seconds. All right, so now what do we do? Well, if you remember, that's assuming 0 less than x less than d1. Well, let's check that. What is our x? Well, x is just v cosine theta times t. And if you plug this in, you'll get an x of 4 meters, which is less than d1. So our initial assumption was correct, and this is just our solution to the system. And if we've gotten something different, like what if we got x equals 8 meters? Well, then we know that there's no intersection because it's out of our bounds. And then we would just use this equation, y equals d2 instead, and then solve it again. And then take the solution that's in these bounds. All right, but anyways, basically, all we need to do, if we go back to the original problem, all we need to do is it asks us where the projectile lands, right? So we already calculated our x, we just need our y. We can plug this into our third equation, and this becomes 2.4 meters. And so that's our solution. All right. And so that's the last problem I've prepared for you guys. And so thank you for listening. And if you go to Morin's book, you can find more problems like these from chapter 3. And as always, if you have more questions, you can ask me. You can go to the YA Discord and ask questions. And yeah, that's it for today. Thank you for listening, and see you next time.